Hello, it's Keith here, and this is lesson 1 of the Absolute Beginners series. This series is going to cover the basics of assembly language and programming in general. Now, what this series is designed to do is it's designed to assist people who found my other series is a bit too quick. I've got a variety of different series that cover programming on particular processors, a tutorial on Z80, 6502, 68000, etc, etc. However, these tend to go in very fast and cover a lot of content very quickly. And for some people who are not so familiar with programming or need a slower pace and a warmer introduction, I've had comments that they are just simply too fast and people can't follow what's going on. So this series is taking a different approach, and rather than covering assembly language itself, this is going into a lot of detail of the concepts behind programming and retro computers, so that when you see those other tutorials, it will be easier for you to soak in the information that's passed in them, because you will have had some background passed you in a slower, more descriptive way. So in this basic series, we're not going to actually cover any commands themselves as such. We're not going to cover any programming examples. What we're going to do is we're going to discuss the concepts of the computer, the concept of the processor. We're going to go into a lot of detail of those kinds of things, and so that when you see those other tutorials which cover the particular processor or the particular computer you're interested in, you will have some foundation to be able to understand them more easily, and hopefully will have a greater understanding and be able to understand them more easily. Now, the contents of this series is based on the first chapter of my book. I've written a book called Learn Multi-Platform Assembly with Chibi Akamas. It's available from Amazon now. However, you don't need the book to understand any of the content in my tutorials. The tutorials are totally self-contained. However, if you want some printed material to read, you're welcome to buy my book. And if you want to support my content, of course, that's a great way to do it. So we're going to be going over the very first things today, and this is going to be referred to as the introduction to assembly. We're going to discuss the very, very simple concepts of assembly language, and also the simple concepts of a processor and what a computer is from the point of view of how you would see it in a retro system. These tutorials are designed to cover old systems from the 80s and 90s. I do cover things like RISC-V and ARM, but I'm generally looking at them from the point of view of the older 8 and 16-bit systems, and so we will be discussing that kind of thing today. Okay. So the first question you might have is, what is assembly language? Well, assembly language is a very low-level programming language. It's in arguably the lowest level programming language. That is, it's the most simple from the point of view of the constructions that are available to us, and also it compiles very, very directly to the machine code that the processor actually runs. So we have a much more limited set of instructions available to us, but because we are building in a very, very direct way to the actual code the processor runs, the result is potentially, if we do it correctly, very, very quick, and there's no slack that we've got left over from the higher level languages. So that is what we have. Now, assembly language, as we would program it, is basically a text file. You can see this text file here. This is the Hello World example from my 6502 series for the PET. Now, there's a lot of code here. We're not going to discuss it, but the point I'm making here is that this is a text file. I'm choosing to edit it with Notepad++, but you can use regular Notepad or any other text-based editor you want. Now, we will assemble this text file into a program code with some kind of assembler. If you want to learn all of this, the best thing to do is go to my other tutorials, the tutorials relative to your platform, the platform you're interested in, the processor, and see the Hello World examples, because I cover how to use an assembler to do that. But you can also download my build scripts from my website, and that will get you started. As I say, though, we're not going to cover the actual code today. All I wanted to do is show you basically that this is assembly and it is just plain text. Now, the assembly program itself will compile to a file. In the case of the PET, we've created this program.prg here, which is a file that our emulator can run. And if I just press F6 and hit enter here, we will start this up on the PET. And here is the PET that has just run that code, and you can see it has shown this Hello World message here. Now, this text file isn't something that our emulator can run because it's not machine code. Machine code is a binary file, and this is the resulting machine code here. Now, you can see the Hello World message in here, as well as some other parts of our program code here. The point I'm making here is that the machine code is literally really just numbers and isn't really very understandable to us us mere humans might be nice for a computer, not so nice for us. The assembly language is a text-based representation of that, but it's a very close text-based representation. A programming language like C++ is a very high-level language, and one command in a language like C++ could end up being dozens of machine code commands in the final file, which makes it very large. So that's the concept of what assembly language is and how it can be assembled. Now, assembly language is going to be a little bit complex for us, so you might have the question, a very valid question, why would I want to learn assembly language? Now, if you've never programmed any language before, my first suggestion would be you probably don't want to program assembly language. I would suggest if you're literally just wanting to learn programming, you would probably want to learn a more common language like C++ or C# or Java or even BASIC. Those are the languages that are going to be easiest and most beneficial for you as a person maybe looking for a career in programming. Assembly language probably isn't the place you want to go. However, if you already know how to program in another language and you're looking to program as a hobby or just as a curiosity, assembly language does have quite a few advantages to you. Now, the first one is that if you want to program a quite impressive little game on an old system, it's got that speed benefit that's available to you. But more as a more educational side, assembly language makes you program in a very different way to other programming languages. Now, I'd program C#, I'd program BASIC, including Visual Basic, and I'd programmed C++ before, and I was reasonably confident with all of those languages, at least to my requirements. However, assembly language forces you to learn things in a very different way, because all of the previous benefits that those languages give you are taken away, and you're really left to fend for yourself, so to speak, and you have to learn how to do things yourself. And also you have to learn a lot more about how the underlying hardware works. You really can't avoid it with assembly language because there's nothing around to assist you, at least in the way I do things. I don't use any plug-in modules. I write all of my own modules to do extra things. So I think that if you know some existing languages, assembly language will give you increased discipline. It will force you to learn things like me personally. I'm terrible at mathematics, and it's forced me to learn more mathematics and become more confident in things like algorithms, because I have to write my own, or at least I decide to write my own, and it will force you to learn more about other pieces of hardware. I've had to learn about sound processors, I've had to learn about graphics chips. All of this comes into scope of what you're going to need to learn. So if you don't want to learn lots of things, then this isn't the language for you. But if you want to take a look at the retro computers, maybe you grew up with these computers and you only ever played them, you're going to see them from a completely different direction when you start doing assembly language. And personally, I've really found that exciting and very enjoyable, and also very practical, because I now have a very good understanding of concepts like binary and hexadecimal and bit masking, things like that, that you wouldn't necessarily have come across if you're only used to programming other languages, or you might have come across them a little bit but never had to really worry about them too much. Well, assembly language will push you to do that. Now, the next question you might have is, what can assembly language do? Well, assembly language can do anything that you can do, because assembly language is essentially the language that all other programming languages end up being converted to. If you've got a program in C++ or Forth or any other language on these systems, and you can compile it to that system, it will end up as machine code, and assembly language is also machine code essentially. So anything that you can do in C++ on a system can be done in assembly language. The only thing is, it's going to probably be a lot more code, and if you're doing things without the assistance of other plugin modules, which is the way I do things, then you're going to have to write that code yourself. So that's what you're going to need to do. And as I say, I personally think that's a good challenge. And you know, if you're writing a program on a 20-30-year-old system, I would say the only reason to do that is for a bit of a challenge, because it's a 30-year-old system. You could write the same game on an Android far easier. So really, assembly language can do as much as we have the willpower to do. So that's what we have. Now, how do you learn assembly language? Well, as I say, I've covered tutorials on the processors themselves. So that is the first stage of learning assembly language. You need to understand the instructions the processor offers. But that's just the processor itself, and we'll discuss the processor in a moment. But the processor itself is just a calculation engine essentially. We will also need to understand the surrounding parts of the computer, and that becomes a very platform specific thing. There is some crossover. The MSX, for example, and the Sega Master System have some common parts, but mostly they're different. I fortunately cover all of these things. I have a CPU based tutorial based on whatever CPU the system you're interested in, the Z80 for a system like the Spectrum, the 6502 for a system like the NES, or the 68000 for a system like the Neo Geo, even the ARM if you're looking at the Game Boy Advance. So I've got all of those processor tutorials, but then you're going to want to look at the platforms themselves, and I have platform specific tutorials that cover concepts like graphics and sound and reading joysticks on all of these systems to get you started on those. So hopefully I've got tutorials out there for everything you're going to need to get you started with a basic level. And on my website I've got pre-configured copies of Notepad++, emulators and build scripts that should get you started on those systems as quickly as possible, with the limitation that I can't give out the ROM files for certain systems. Like the system like the Neo Geo, I can't redistribute the ROMs. But as I say, basically I've got the assemblers and emulators and build scripts all pre-configured, along with examples of hello worlds and things like that to get you started. Okay, so that's what assembly language is. That's why I think you should learn it, and that's what you can do with it. The next question we're going to discuss today is what actually does a retro system look like? And like I'm sure most people, I have massive piles of old retro junk lying around my house. And it just so happens I happened across this Neo Geo CD board. I bought a Neo Geo CD that was cheap. It actually didn't work, but it did come along with lots of joypads and power supplies and things that were often missing from other ones, so it was still a bargain. Anyway, I thought we'd have a look at the motherboard of this system because, like most of these old systems, it's split out into lots of chips. On your modern systems, you often hear the phrase system on chip, and that might mean that the entire system is on just a single processor, which is quite boring and hard to explain, but these old systems are really split out. So we're going to have a look at the Neo Geo CD, and we're going to have a very simple discussion of the kind of areas of the system that you will see. And although we're looking at the Neo Geo today, I've split out the sections into the common concepts that most systems will have, and really this is just to give you an idea of what an old system looks like, literally at the hardware level because we're looking at an actual board, but also from the point of view of how the functionality of the system is split out, and you will need to understand that if you're trying to program it. So we're just going to discuss this as concepts today. Anyway, let's go over and have a look. Okay, so here is our Neo Geo board here. So this is the board itself, and we're going to go through the various sections of this system, and we're going to look at what some of these chips do. Now we're going to look at a simplification of this today, but what I'm telling you is basically true. I'm just oversimplifying a little bit for practical purposes. So first of all, we've got the main CPU. Now the Neo Geo uses a 68000 processor. It's a 16-bit processor, and it's actually not the biggest chip on the board, which personally I might have thought was a surprise, but actually it's not. But let's say that is our main CPU on this system. Now the CPU doesn't have much storage within it, so it has a RAM chip, that's random access memory. That is for the storage of our temporary variables, things like that, maybe the player's position, the map of the level, things like that. They're stored in RAM. We also have a ROM chip that is read-only memory. RAM can be changed, but read-only memory cannot. So the ROM chip on this system is basically the firmware. When you turn your Neo Geo on, it says Neo Geo 330 mega pro gear spec or something like that. That is all done by the ROM chip, and the ROM chip also has the operating system and things like that. Now some systems like the Sega Master System don't have any ROM, but the vast majority of them, especially home computers like the Spectrum, the Amstrad CPC, the C64, all had some kind of built-in ROM. Now in addition to that, we've got an I/O chip. Now the I/O chip on the Neo Geo is incredibly large. In this case, I think the I/O chip is probably linking to all of the other processors on the board. But often on a retro system, an I/O chip might do things like connect to the joysticks or the keyboard, for example, maybe connect to the sound card. I/O input-output is going to be essential for communicating from our processor to other parts of the system or external devices. So we're going to see some kind of representation of that in all cases. Now on the Neo Geo we have an audio chip. This is an AY compatible sound chip. Some systems again may not have audio in the same way. Some of them don't have audio at all, some have much more simple audio, but there's typically going to be some kind of sound processor, and the point I'm making here is it's separate from the CPU. The CPU can't make sounds, so don't go looking around in your 68000 manual for sound programming guides or for sound commands. There aren't any. What we have to do is we have to tell the 68000 CPU to talk to the sound chip and tell the sound chip what we want to do. And the thing that's important is, as I say, is we need to look up our hardware, our platform-specific documentation, find out where that sound chip is, how we interface with it, which will vary depending on the system, and then we need to look at the documentation of the sound chip and work out how to tell that sound chip to make the sound we want. Maybe we want to make a high-pitched beep, or maybe we want to play a speech sample. But all of that's going to be dependent on this kind of sound chip. And as I say, in my tutorials in the platform-specific series, depending on the processor and the platform, I have basic examples for making little beeps and things, so I can get you at least started with that. But as I say, it's totally separate from the processor, and that's the important thing to notice here. Then on the Neo Geo CD, we've got video processors. We've actually got two of them. The vast majority of basic systems would only have one graphics chip, but in this system we've got two. Now, again, I'm not going to go into what they particularly do, but the point I'm making is, once again, on this system, the graphics is separate from the main CPU and separate from the main memory. Now, some systems like the ZX Spectrum or the Amstrad CPC, the main memory is actually the video memory, but on the other systems it's not, and there's a separate chip that, once again, we need to talk to. Once again, we will need to look at our platform-specific documentation. There's nothing really you need to remember here. It's just to make the point that a system is split out and to give you an idea of the ways that they are often split out. And you'll come back later and you'll start to look at the specifics of the system you're interested in, and hopefully you'll just remember back to this, and you'll start to have a bit more of a concept of expecting to see maybe the memory of the main processor and the video memory being split out. And that's what we've got next. On the Neo Geo CD, like most systems with video chips, the video memory is split out from the main memory, and that will mean we will probably have to talk to the video chips to access that video memory in some way. And again, that's the point that I'm making here. So you can see that this system is very split out. Our main processor has RAM to talk to read and write, ROM to read from and maybe to do other functions for our processor, a sound chip to make sound, video chips to ask to do things with graphics, video memory which we may need to change what's visibly shown on the screen, and an I/O chip to talk to other devices and other parts of the system. Now, all of that is just a very basic example of the kind of simple concepts that you might see in a system. And here's a really more cartoony version of the similar concept. As I say, you will often see a system split out in a way like this, and this is the exact same representation, just as a drawing rather than as an actual piece of hardware. But I thought it'd be more interesting to see a literal piece of hardware and prove that it wasn't just an unrealistic concept, it is literally true. So that's what a system might look like, and that's a very rough discussion of the way a system is often split out. You don't need to remember any of that, as I say. It's just to give you a basic foundation for when we start to discuss other things. We're now going to discuss some very simple concepts of a processor itself. The first question is, what is a CPU? Well, CPU stands for Central Processing Unit, and the CPU is essentially like a calculator. The CPU will essentially do mathematical calculations for us, and then we will be able to do things with those calculations. Now, as systems get newer, they've become more powerful, but the very early systems really couldn't store much data in the processor at all. They could really only maybe store the result of the last calculation. So you can think of your CPU like your calculator, which can only store the result of the last calculation. Well, what do we do? Because obviously we're going to need to store more than one calculation at a time. We're going to need to maybe calculate the X position of our player and then the Y position of our player and then draw it. Well, where are we going to store this data if we can only store one calculation at a time? Well, the answer is our memory, our RAM, random access memory. And so you can think of your CPU as your calculator for calculating the current thing, and your memory as in this case, a notebook. I've drawn it. You can think of this as the sequence of results, the various results that you're going to want to use later on in your program. Okay, well, what is our memory? Well, I think the best way to think of memory is as like a series of lockers that are numbered. Now, on an 8-bit system with a 16-bit address bus, the lockers would be numbered from 0 to 65535, and each of these could store a message of a single byte. So each of these has a number, and we would go to these numbered lockers and we would either put something in them or take something out of them, in each case 1 byte of data. So that's what we've got represented here. You can see we've got our numbered lockers here, and each one can contain some data. So these would be the values that our processor has previously calculated. They would also be things like maybe our game map, if we've got a Super Mario type game and we've got a level planned out, the position of our Goombas, the number of lives left, all of these would be at various memory positions. Now, on some systems like the 6502, parts of the memory may connect to other things like the sound chips, for example. But that's really beyond what we need to worry about today. The only thing you need to know at this point is that memory addresses are numbered positions, and each one has data in it that in some cases, if it's RAM, then we can write, or if it's ROM or some other memory map device, it might be read only. But you're going to see all of that when you look at the processor specific examples. So that's memory, and in most cases we're going to be probably considering random access memory, things we can read and write to. That's of course RAM, but there is of course the other kind of memory, which is read only memory, ROM. And as I said before, the ROM is going to be our operating system, probably on a system like the Commodore 64. It's going to be our bootstrap on a thing like the Neo Geo. And there will be various things that may help us out with our programming, but the RAM is going to be the part of the data that we can actually change and store as our results of our programming. Now, the CPU can connect to both of these, but of course it can only read from the ROM. Now, the final thing we're going to discuss today is the concept of registers. We're only going to go into these at a very simple level today. Basically, we've got our processor, which, as I say, is like a calculator, which can only store a few results, or maybe even just one result at a time. And then we've got our RAM. Now, the only thing is that although our RAM is a big store of memory for storing our results in, the processor itself does have a very, very small amount of memory in it, and this is known as the registers. Now, the amount and size of the registers that the processor has will vary depending on the processor. Some processors just have 4 registers, some have 32. It really depends, and an 8-bit processor usually only has 8-bit registers, whereas a processor like the ARM has 32-bit registers. It really varies quite wildly. What doesn't vary though is that the processor has a very small number of registers compared to the amount of memory it will be typically able to address. A system may only have 4 registers but be able to access 64 kilobytes of RAM. And well, what's the advantage of the registers then? Well, the registers are extremely fast. Now, we might be able to use our general memory as the source and destination of our calculations, but to do so will be much slower. Now, if we just go back to the Neo Geo board here, this is our main CPU, and this is our memory, and there is a physically large distance between the two, but the registers are actually literally contained within the processor itself. So it's going to be much faster to access those registers than to go out to the memory. And that's why the registers exist. They're the very, very fast store for the intermediate calculations, and then we store out the result back to our slower RAM, which is much more available. And that's the reason we have the two, and that's how we need to use them. We want to use our registers where we can. Where we don't have enough registers, we need to go back to our RAM and store out some of the registers and clear them out and do some more calculations. Anyway, that's all we're covering today. Now we're going to be coming back next time, and we're going to look more into the CPU. I hope you found this interesting. If you've found it a little bit difficult, you want a more slow-paced one, please go to the website and see the text-based content there. It covers all of the descriptions in a more formal way, and so please read that if you want more details there. If you're feeling adventurous and you want to really crack into it, please take a look at the processor-specific series for the processor you're interested in, or the Hello World series, which shows a simple Hello World on the platform you're interested in. Generally, if you search for Chibi Akuma's Hello World and the name of the system you're interested in, assuming I've covered it, you should find it. Anyway, I hope you've enjoyed this. If you have, please like the video. YouTube recommends videos to more people based on how many likes they've got. So if you like the video, it will be shown to more people. And also subscribe, because that will show you the next video, and it will also encourage me to keep working on my tutorials, because I've made an awful lot of tutorials and I'm hoping to make an awful lot more if people enjoy them. Anyway, thanks for watching today, and goodbye.